Hello, and welcome to this special one-hour programme. We're here at the Institute of Astronomy in Cambridge, and we'd like to take a moment to look at the past and future of the state of astronomy.
As a new decade begins, we've invited 6 distinguished astronomers to join us as we look back at the revelations and milestones of the past 10 years.
And with a host of new telescopes coming online, we want to ponder what discoveries will swim into focus and what will be the burning questions that astronomers will be facing in the 2020s.
Welcome to the Sky at Night.
Incredible, exciting.
That was one that I slightly missed because I was on maternity leave.
No one believed him.
You're not allowed the whole solar system. You have to leave some of it for other people.
Nice.
We asked our 6 guests to look back at the achievements of the past decade, to tell us what they found most significant, surprising, and what had the most impact.
From the University of Oxford.
Gosh, it's been a good decade, hasn't it? It's fantastic. And phosphine, yeah.
We'll be asking our guests what discoveries might be lurking just around the corner and what they think are the most pressing questions for astronomy in the coming decade. We've also got questions sent in by you, our trusty and ever-curious viewers. So observe closely as we investigate the state of astronomy.
When you were walking along the astronomical wall of discovery, there were some things that caught your eye. What in the last decade has really made you thought, yes?
There's a couple of things in the last decade that I go, wow, that's the universe. That's amazing. And one of those things was gravitational waves. And I was like, what is this?
We've got the small topic of the last 10 years of astronomy and the next 10 years to talk about. So where shall we start?
When I think about my highlight from the last decade, it's got to be the direct detection of gravitational waves for the first time back in 2015. That's an absolute top highlight for me.
Gravitational waves. Finally detecting those gravitational waves arriving at Earth from merging neutron stars and from merging black holes. That's been a discovery waiting for about 40 or 50 years.
Gravitational waves are ripples in space-time. These are from the merging of two massive compact objects, and they send off the equivalent energy of about 3 times the mass of the sun in the form of these gravitational waves, these ripples in space-time.
So just from one event, it's the same as getting all the energy from 3 lots of suns.
It's incredible, isn't it? 3 times the mass of the sun being sent out across the universe in this very short event at the point of them merging, and then being picked up by these detectors here on Earth eventually.
This can be modelled by computing what Einstein's theory says should happen. And here again, this I would say is the strongest confirmation that Einstein's theory works even when the gravitational fields are strong and rapidly changing. The LIGO experiments are a huge achievement, in my opinion, not only for their science, but for the technology, because it's really amazing, because you have these mirrors which are separated by about 4 kilometers, and what happens when a gravitational wave goes by is that these mirrors shake. They're pulled in and then out by a tiny, tiny amount. And to measure this tiny motion is a huge achievement, because it's a millionth of the size of an atomic nucleus, and the precision is like observing something the thickness of a hair at the distance of Alpha Centauri. It's amazing technology. We're
up to 50 detections now, and if you think back to 2016 when this first one came out, and then the next few announcements, each direct detection of gravitational waves was its own press release, its own announcement. Everyone got very excited, and now they've just released a whole bunch of them. You know, we're not announcing individual ones anymore. It's catalogues, it's databases of gravitational wave detections.
Previously, astronomy for the last millennia has been looking for photons, looking for light. The electromagnetic spectrum is everything. We interpret it in so many different ways to learn about the universe. Now we can understand it that way as well. It's a whole new realm has opened up. So that's just blows my mind that we can just listen to that little chirp and go, oh, something just happened over there.
It's 2 big things just away to that. Talking about things in the solar system, what have been the discoveries there that have made you excited?
Obviously, we had the end of Cassini, which was sort of a sad moment, but a nice celebratory moment as well, to think of everything that showed us on Saturn. Saturn is my favourite planet, so maybe I'm a little bit biased, but the images that Cassini sent back of sort of the hexagonal storm, of its moons and everything, I think that will have a very long-lasting legacy.
So, yeah, it was a sad end, but it was just sort of an exciting, a suitable tribute, I think.
Yeah, I think so too.
For lots of us, a big part of astronomy in the last decade is the exploration of Saturn and its moons by Cassini. Tell us why Cassini was important and what you think it achieved.
I think Cassini was important for a whole range of different reasons. Because it was going into orbit around Saturn, it meant it could spend enough time there. And once we'd spent the first 4 years in orbit, we were then able to decide what it was we wanted to focus on for the rest of the mission. So there was a real focus on the moons. And then at the end of the mission, there was a real focus on Saturn. And you will remember that we essentially ended the mission by diving into the atmosphere of Saturn.
Yeah, and it is a spectacular way to end a mission.
Absolutely. So we didn't want to crash land Cassini on a moon where we might find life in the future. We didn't want it to crash land on Titan or on Enceladus.
This is the great result, of course, from Cassini, is the moons and their varied nature and their potential as life-bearing places. Tell us what we know about Enceladus now.
By the time we got to the end of the Cassini mission, what we know about Enceladus is a huge amount. We know that there's this outgassing of water vapor plumes from the South Pole, and this outgassing is coming out of cracks at the South Pole, which the imaging team called tiger stripes. There is internal heat leaking out. There is also organic material in the plumes. and there is a liquid ocean under the surface. And so it's got three of what I call the four ingredients that you need for life to potentially able to form. You need there to be liquid water, you need there to be a heat source, you need organic material, and then the fourth thing you would need is those first three to be relatively stable over a long enough period of time that something can actually happen. And so that is really why there's such a focus on Enceladus now for potentially sending future spacecraft to see whether we can actually get much closer, go into orbit around it. But it's difficult to do at Enceladus because it's a small moon. Its diameter is 500 kilometers. So that means...
I always think it's about the size of the UK, right?
Yes, yeah, that's right. And so that means that its gravitational field is low. So you need a huge amount of fuel to be able to get into orbit.
We mentioned Titan, and what we really saw over the last decade, the last half of the Cassini mission, was Titan as a world. Tell us what it found.
Well, I think for me the most exciting part of the Titan journey was the fact that for the first 4 years we didn't see liquid on the surface of Titan. Now, we knew there had been liquid on the surface because when the Huygens probe traveled down onto the surface through the atmosphere, we saw all these river beds. But we finally saw liquid on the surface. There was the glint of the sun off an ocean at the North Pole.
But this isn't liquid water, is it? That's important to say that earlier.
That's right. This was liquid ethane and liquid methane. And it turns out the reason we hadn't seen it before that was it was the dry season on Titan. There hadn't been...
Turns out there's a dry season.
Yeah, there hadn't been any rain falling. There simply wasn't any liquid on the surface. And since then, we've now found huge lakes.
We also have Juno, which is in orbit around Jupiter now, and just the images alone are gorgeous. They couldn't do the orbits they wanted to for Juno because the magnetic field was so strong, it was damaging the instruments, and they had to keep it in this really wide orbit instead of going closer to the planet. But what they've been able to do with that wide orbit is actually measure the gravitational pull better. So we've missed out on some really gorgeous things about the clouds, but we've learned way more about the interior of Jupiter because it couldn't do what we wanted it to do. And the science we're getting from that is helping us understand if Jupiter has a core. And that's kind of crazy that we don't know that.
But I suppose that big puffy atmosphere sort of obscures a lot.
And I think it's really important to understand that there's still unknowns in our own back garden.
What other things strike you?
The New Horizons flyby of Pluto certainly is up there, you know, seeing those images of the surface of Pluto for the very first time. I just wish that it could have orbited.
The images from the New Horizons mission of Pluto have turned it into a world, a fully formed, dynamic world, which also has an atmosphere. And we were like, what? How?
Not just a lump of rock a long way away.
No, it's got formations, it's got geography, it's got movement, and it's got an atmosphere. And there's so many things that we still have yet to discover in our solar system.
Now, you are interested in galaxies and their interaction with black holes. Over the last 10 years, what have we learnt in that area?
The big thing for me for the past 10 years was the fact that we got this first ever image of a black hole from the Event Horizon Telescope. And I remember as a kid, I would hoard space books, and the first thing I would do would be to turn to the page on black holes and just take in every single piece of information I could. But I was always sort of disappointed that the image on those pages would be an artist's impression or a simulation or something like that. And I knew that, you know, because of black holes, you know, sort of trapping light, you know, nothing can, you know, travel fast enough to escape a black hole. I knew we would never get an image of a black hole. That was sort of what I disappointedly resigned myself to. And I didn't think that we'd ever get to see something like that until the day they actually released it. And there it was. And it was just... I was speechless, you know, I was absolutely mesmerized by this image. And I remember, you know, people being like, oh, is that it? That big orange donut, you know? And I was like, yeah, it's a big orange donut.
So you waited a long time, but it lived up to expectations.
Massively so, yeah. I mean, I was expecting something that was like 4 fuzzy pixels or something, you know? So the fact that we had something that was resolved and with structure in it, I mean, it gave me like goose pimples. And I remember someone saying, you know, what's the difference though between sort of the black on the outside of the image and the black on the inside of the image? And that's what's so beautiful about that image to me, is that the black on the outskirts is, you know, the vastness of space. It's just nothing. Whereas the black on the inside is everything, you know? It's as much mass as you can get, it's just as dense as you can get it. And that's what, you know, makes that image so incredible to me. And I think when you then start to think about how much team effort and collaboration went into that, bringing together telescopes from across the entire world, you know, even on the South Pole, to get that image, and then all the processing of the data as well that went on afterwards to produce it. It really is just, it's a triumph of just humans coming together and working together, isn't it, really? And then you have just this incredible thing to look at the end, too. It's beautiful.
Because I really feel that space astronomy can do that. Sort of, yeah, we're united, and then we look out there, and together we can see some amazing stuff.
Well, exactly, because, I mean, that is one thing that unites the world, right?
We've got to talk about Rosetta, surely.
We've got to. Can you say the name of the comet, because I still can't get it?
Sure, this was the mission to comet Cheremeyev-Gerasimenko.
There you go.
Chewy gooey to its friends, yeah.
The Rosetta mission with the Philae lander, which I feel that really just captured the public's imagination. I've never seen anything like it. The way that every school I went into, the kids wanted to talk about Rosetta. You know, random friends who've never shown an interest in astronomy wanted to talk to me about it. Yeah, they did a fantastic job with capturing the public's imagination with that one.
Can you remind us of the story as that played out?
Yeah, so this was the first mission to do a soft landing on a comet, the Philae lander. It was all very dramatic, wasn't it? Like watching the images of Philae being dropped from the Rosetta spacecraft. And then instead of making that nice soft landing, the harpoons that were meant to fire into the surface to anchor it didn't work. And so it landed and bounced and then landed again and then eventually came to rest. And it took a couple of years until that landing site was found.
So why is it that you think people did have this interest in Rosetta, this particular mission?
I think those cartoons was a huge part of it, wasn't it? The social media presence and the web and media team in that mission in general, they did such a good job of kind of humanizing both Rosetta and Philae, making them into these characters that we could feel a connection to. And I certainly remember shedding a tear when they put out the final cartoon of Philae saying goodnight, and yeah, it was very emotional.
In your field, what has been the amazing stuff of the past 10 years?
Exoplanets are insanely new. And in the last 10 years, we have gone from knowing that there are just 500 exoplanets out there to over 4,300. 10 years, we've almost 10 times the number of planets, which is just insane to think that we didn't know that they were there. Almost every star that you look up probably has a planet around it, and that's an amazing thing to realize, and that happened in the last 10 years. And a lot of that is thanks to a mission called the Kepler Space Telescope. And this is a NASA mission that stared at over 500,000 stars. And it was looking to see the tiniest change in the light of those stars, which signified that there was a planet that's orbiting that star that passed in front of it and blocked part of that light.
The other highlights for me was definitely the Kepler Space Telescope. It's just incredible. And I think, you know, if I didn't work in galaxies or black holes, I think planets could sway me.
So exoplanets, you'd be tempted out there.
Yeah, and maybe even Saturn could sway me to work in the solar system as well, maybe.
Yes. But you've taken it further, because you look at the atmospheres of exoplanets. Now, when I first heard about this, I thought, this is the science of the impossible, but this is what you do.
Yeah, I love the fact that these planets exist, but I want to know more. So what I do is I look at planets and their atmospheres specifically, and I'm looking to see what they're made of. And I do that by seeing these planets. Again, these are the ones that are passing in front of their star that I look at. And if they've got an atmosphere around them, some of that star's light's going to shine through that atmosphere before it reaches us. And from that, we can measure what that atmosphere is made of. We need the biggest, puffiest atmospheres possible. I love a good giant gas planet. Big gas planet.
Puffy atmosphere. I'm going to take that away.
Big puffy atmosphere. And those are the ones that we're really able to investigate right now. And the Hubble Space Telescope, which is now, you know, it's 30 years old now. It's crazy. 30 years old, and it's still doing brand new science. And that's what we're using for a lot of the investigations we're doing to understand what's in these planetary atmospheres.
One of the big things that I think is exciting, and I think will continue to be exciting, is the Gaia mission. And that's a mission I've been very closely involved in. It's like a tidal wave going through astronomy. Last year, there were something like 1,600 scientific papers published using Gaia data. That's actually more than published with the Hubble Space Telescope, which has always been the most productive telescope in the world until that point.
So what do you think are the highlights of Gaia? What is it really given us?
I think it's the knowledge of the structure of the Milky Way, how it's built up from its constituent components.
One of the things I love about some of the early data was the prediction of where stars in the galaxy will move. And so you can see how the galaxy evolves. And so I just think it's magical to see the movement of billions of stars in our galaxy, where they'll be in the future.
Yes, and we've just had the third release of the Gaia data catalogue, and there are some fantastic results. One of the things that we're publishing from that catalogue is a general catalogue of nearby stars. And we can see essentially that we're at a cosmic crossroads. And the stars that are near us now won't be the same stars in a few 100 million years, as everything rotates around and moves at slightly different speeds. And in fact, one of the remarkable discoveries from this latest release of the Gaia data is the fact that the solar system is accelerating in space. It's being pulled in a particular direction. And that's something that we would never have anticipated discovering or knowing about without the Gaia catalogue.
In cosmology in particular, we do have these elephants in the room in that we don't know what dark matter is. And there's this thing called dark energy, this acceleration that we don't understand either. Do you see any progress in understanding those big questions, what the universe is made of?
Well, of course, as you say, ordinary atoms are only about 5% of what's in the universe, and there's about 6 times as much dark matter. And as far as we can tell, this behaves like a swarm of particles, which have no electric charge and just interact by gravity and also don't collide.
And they don't form dark matter planets or anything
No,
like that? They don't clump
that's
in
right.
that sense.
That's right. So they don't radiate light or heat. But of course, there was always a hope that we wouldn't know what they were. In particular, it was thought that the Large Hadron Collider, the big accelerator in CERN, would discover a class of particles which had the nickname WIMPs, weakly interacting massive particles, and some theories predicted these. Now, that didn't happen. The LHC didn't find any of these particles, and so we might detect them by bigger accelerators. And there are some rather more exotic ideas. There's something called fuzzy dark matter, which would be particles of tiny, tiny mass, where the quantum uncertainty, their position, because their mass is so small, is itself on the scale of a galaxy. So that's the dark matter. What's now called dark energy, I would say, is more of a challenge, because the expansion of the universe, which was expected to be slowing down because every galaxy exerts a gravitational pull on every other one, in fact, it's speeding up. And so there's a repulsive force latent in empty space, and it's telling us something about the nature of space itself. But I think it's going to be very, very hard for us to understand this until we have a unified theory which brings together the forces of the micro world, electric, nuclear forces, etc., with the force of gravity which dominates on large scales. And that will require having a theory which we can actually test by showing that it has consequences in the everyday world. So although I think we may pin down a bit better what the so-called dark matter is, I'm not at all optimistic about how quickly we will understand this so-called repulsive force or dark energy.
Meanwhile, in another corner of the cosmos, still very much in the dark, yet full of energy, here's Pete.
No, I may be mistaken, but the sky is clear. I've forgotten what a clear sky looks like. There's a little bit of low-level cloud. There's a beautiful crescent moon behind that low-level cloud. Hopefully it'll come out in a minute. But above it, and slightly to the left at the moment, I've got two bright planets as well. The brighter one is Jupiter, fainter one is Saturn. And if you've been looking at them over this year, they've been visible for many months now, they've been gradually getting closer together. Now that apparent movement together will actually reach a crescendo on the 21st of December, because then you're going to have what's known as a great conjunction, and they'll be just 6 arc minutes apart. That's 1/5 the apparent size of the full moon. I'm going to take some pictures tonight and see what I can get. Okay, so I've got my DSLR camera. Helps if you turn it on. There we go. So there we go. I've got the moon and I've got Jupiter and Saturn clearly in view. And I'm going to take the shot. 2-second exposure. And there's lots of clouds down there, but it's picked out the moon. There's a plane going through the field of view. There's always a plane going through the field of view. There's the moon. And there's Jupiter. And there's Saturn. The last great conjunction was about 400 years ago in 1623. So it's quite a special event. You should be able to see it with the naked eye. It'd be interesting to look at and see whether you can actually split those two planets. A pair of binoculars will pull them apart quite easily, and a telescope using a low power eyepiece will show both planets as disks in the same field of view. You know, seeing both Jupiter and Saturn in the sky fills me with a sense of time, because they're both quite low down in our sky in the UK at the moment. This year they've been horrendously low. As the years go on, then Jupiter will gradually start to climb up. Next year, for example, as we go into July and August, Jupiter will be more or less twice the altitude it has been able to reach this year. So that's pretty good, because it moves it out of the murk. But Saturn is slower, so we'll have to wait a number of years yet before Saturn gets to an altitude which puts it in a good position for UK observing and viewing. And it's quite humbling when the universe does that, because the universe goes at its own rate. It doesn't entertain us. It just carries on as it wants to. Technology, on the other hand, moves at quite a pace. And there have been dramatic changes in the equipment available to amateurs over the last decade. telescopes have become more affordable, their mounts have become more sophisticated with more and more computerization being added to them. But one of the biggest changes for me, because I'm interested in observing and photographing the sun, has been the affordability of devices like this. These are hydrogen alpha filters, which allow you to look at the sun safely and pick out the light given out by excited atoms of hydrogen. And you can see things like prominences, which are huge clouds of hydrogen gas hanging off the edge of the sun. But one of the best changes really has been the development of high frame rate, what are called planetary cameras. Now basically you stick those into your telescope and the camera will record a sequence of still frames and it will collect them together in a movie file. And the idea behind that is that when you have distortions caused by the Earth's atmosphere, the seeing has periods where it goes nice and steady. Very short periods. So the object you're looking at looks nice and crisp. So in this collection of thousands of frames which you'll have, some of them will look like they're supposed to. And using special software, you can extract those frames, you can average them together, and you get a result which is much better than you thought you would have got. So all this technology is constantly evolving. It's actually quite affordable these days. So it's really interesting to think where it's going to end up in another 10 years' time.
For some of that, I wasn't actually on the sky at night. So.
No, you appear about here, I think. This is. We should have that.
Yeah, no, a little capsule or something.
That's right.
Gravitational waves, to me, was the biggest game changer of all. It seems like impossible science, and yet they've done it. I love the collaboration, people working together.
And we haven't talked about Pluto, look. I hadn't really thought about what it'd be like to have a flyby. Like You get this image and then that's it. The spacecraft disappears. Not like Cassini.
I
that's up there.
know, that dwelled. So we've got the decade of astronomy, but what do we call the decade? I mean, is it the teenies?
I'm looking forward to the letters from everyone. The new decade, does it start in 2020? Does it start in 21?
2021, yes. There was no year zero.
Right.
So a decade should go from 1 till 10. And so that would mean that 2020 was the start of the 20s, but the decade starts in 2021.
Fine, so we can make this program.
Yeah, I think we're okay. As we take stock of the changing of the decade, and with a constellation of captive astronomers, we put to them a selection of your most probing questions. Here's a question from Ian Higginbotham in Aston-under-Lyme in Greater Manchester.
He says, my son Hamish, who's aged 7, and I are both avid stargazers, and I always emphasise the importance to Hamish of how do we know type questions.
Recently he asked me a question which I struggle to answer. How do we know the sun is a star?
That is a fantastic question.
One thing I'm not quite sure about is which came first. Did we say that all stars were like the sun, or did we say that the sun was like other stars? I'm not quite sure.
The reason why we know the sun is a star is it is doing all of the things that we think stars do.
We know it because we can study the light that we get from the sun, and we can also, with a telescope, study the light from other stars. And it's very similar.
It's fusing at its core, hydrogen. It's pushing it together, and that's giving off energy in the form of this light. So that is the fundamental thing that a star does, and our sun does that in a beautiful abundance because it lights up our daytime. So we know the sun's a star because we see that it's giving off and emitting its own light.
So the next one's just for you, from the Reverend Jeff Brown in Welwyn Garden City, and he says, in 1968, when we were both young, you came to dinner at Westcott House in Cambridge, where I was training for the Anglican priesthood. After dinner, in an open forum, I asked you if you thought the universe was infinite. You replied cautiously in the affirmative. Would you, half a century later, respond more cautiously or less?
I'd still be cautious, and I think this raises a very interesting question. We know that the part of the universe we can see is almost certainly a tiny fraction of physical reality. There's a sort of horizon set by how far light's been able to get to us since the Big Bang. And moreover, I've come to believe since 1969 that it's possible that our Big Bang was not the only one, and there may be many Big Bangs. even an intricate kaleidoscope, as it were, of separate cosmoses. So I think that even though the universe may not be infinite, I think with great confidence it's much, much, much bigger than the region accessible to our telescopes.
I'm glad what you said after dinner made such an impression all that time ago. I hope people remember that answer too. Next question is from Simon Bakewell in Denby Dale in West Yorkshire, who's imagined a system. He says, if a planet exists in a binary star system...
Is it possible that it could orbit both stars in such a way that there is only ever daylight sunlight on the planet?
If that's the case, any intelligent life on the planet would never see the night sky and know nothing of the stars, and therefore have no incentive to explore.
Ooh, good question.
What would have to happen is it would have to be orbiting the star. I'm looking up because I'm trying to work it out.
Oh, yeah, picture it, yes.
I think actually the answer is probably no.
I don't know, you know.
Yeah, I guess that planet would have to be permanently in between the two stars. And so that could actually be possible because there is some points. So we have the similar thing in the Sun and the Earth orbit. We call them Lagrangian points. And so there are very specific points that if you put something there, it would stay there because it'd be kept in what's called this three-body system, the Sun, the Earth, and say a satellite, like the James Webb Space Telescope, that's going to be at one of these points. And so the same could be true of a planet. It could be trapped in one of these points in this system that would keep it in place so that both sides of the planet would always be lit by either star.
Well, the problem of being a planet in a binary system is that the orbits often are unstable. And the main constraint is that, of course, for life to exist, conditions have to be fairly stable.
It will be very hard to keep it in that position. I think it just wouldn't be stable
Any small
enough.
perturbation and it would... Whee!
Probably crash into one of the stars.
But one related point I would make is that there's a very interesting planetary system called TRAPPIST-1, where there are planets orbiting a very, very small star, and the outer three of those are habitable, but they are tidally locked. And that means that they present their same face to the star, just as the moon presents its same face to us all the time. And so if you are on one of those planets, then half of the planet would be in perpetual daylight, half in perpetual dark. So if there was intelligent life there, then everyone would be in one half except the astronomers who'd segregate in the other half of the planet.
Sounds perfect to me. The next question then is...
Shani Mazunda, age 15, from London, wants to know, what drives the spin of orbiting objects?
Oh, don't get me on angular momentum, Chris.
How long have you got for me to answer this question? this could take a while.
So when a planet system is forming, a star, all of the matter is gravitationally pulling together and the star forms out of that, and that's spinning.
So then you've got to think, well, where did that gas cloud get that little bit of movement from in the first place? And it's this sort of hierarchical, like, where did everything inherit its spin from? And I think it all comes from the very beginning of the universe, the very early universe, where you just had this random soup of particles. And there was all these random motions. Those random motions will have at least given something a kick back then in some direction as you first started to form the first stars and galaxies. And so everything, the reason that we're orbiting around the sun will have been inherited right from some random motion at the beginning of the universe.
Here's one from Bill Foote in Weymouth in Dorset. Is it reasonable or possible
that dark energy and dark matter are the influence of other universes on our own universe, but we don't have the technology to detect them? He says the sky might not be the limit.
Well, I certainly agree with that last statement.
That's almost a philosophical question, I always think, than a physics question.
Well, I certainly agree the sky is not the limit. I think there's far, far more beyond our horizon than inside.
There are physicists, cosmologists who are working on trying to figure out if you'd ever be able to detect the effects of different universes. Certainly this idea of multiple universes isn't a completely out there science fiction.
There's a number of different theories which say that we are kind of just a universal bubble, and next to us there are other bubbles. And
I personally think that, we don't know about dark matter and dark energy enough to really rule out any kind of theories like that.
We don't really understand the dark energy, and when we understand it, we will know more about what might lie beyond what we can observe, and we could then perhaps answer the question better than I could now.
Excellent, thank you. It's certainly been a remarkable and exciting decade for astronomy, with breakthroughs that we could only dream of just 10 years ago.
But what of the future? What will the next 10 years bring? Well, with a host of space and ground-based telescopes coming online and a flurry of space missions, the 20s is looking pretty exciting. What's coming up in the next decade that you're excited about?
Right now, we are at the cusp of masses of data coming in. There are instruments coming online which are going to overwhelm us with data.
Yes.
And the James Webb Space Telescope is one of the biggest ones because it's going to change a huge range of astronomy, not just exoplanets, but we're going to look further back in the universe than we have ever looked before.
There is lots of good stuff on the horizon. Something that I'm fairly closely involved with is the James Webb Space Telescope. Hopefully we're now on track for a launch towards the autumn of next year.
The big question that I care about a lot is, how do black holes grow? How do they form in the first place? And it really leads back to something I like to call the astrophysics chicken or the egg question, right? We have a supermassive black hole at the center of every galaxy. So the chicken or the egg is whether the supermassive black hole formed first, maybe perhaps a giant gas cloud in the early universe collapsed, and then a galaxy of stars formed around it. Or did a galaxy of stars, a collection of stars form first, one of them go supernova, form a black hole, that started to grow, became the heaviest thing, and then it was the thing that everything orbited around in the galaxy. And amazingly, I think in the next 10 years, we might be able to answer that question, and that's because of the James Webb Space Telescope. It can see further and fainter than anything it's been able to see before. So because light takes time to travel to us, we can see earlier and earlier in the universe. And so we can look for these signatures of these collapsing gas clouds or these growing sort of black holes from what I'd call a piddly black hole, right?
Who knows what it's going to find? The James Webb Space Telescope is going to be looking back so much further in time than Hubble was able to as well. So we're going to learn a huge amount from the formation of our universe down to the smallest, tiniest little planets and asteroids in our solar system.
I do have one thing I'm not looking forward to at all, and that is the fact that this decade is the decade we will probably say goodbye to the Hubble Space Telescope. I have a really odd, kinship with the Hubble Space Telescope because it was launched a month before I was born. So I have never known a world where Hubble isn't somewhere above our heads, taking those spectacular images that I, grew up with, turning the page of the newspaper and seeing, the Eagle Nebula in all of its glory, or some incredible galaxy that's been seen. And I use it as part of my research as well. And so the fact that it might run out of fuel and we won't service it, and eventually it will actually come back down to Earth. Yeah, I'm going to shed a tear that day. I really am going to shed a tear.
There are some fantastic projects coming along, so hopefully we'll be able to fill the gap.
Yes, exactly. We've got James Webb Space Telescope coming. Then we've also got the extremely large telescopes, so the 30-metre telescope, the Vera Rubin Observatory. There's lots of new observatories coming. But there'll still be a little hole in my heart where Hubble
won't have
was.
the same place in your heart.
No, they really, really won't.
Sitting here at the end of 2020, away from Saturn, what do you think are the big unsolved problems in understanding our solar system?
I think for me it goes back to habitability. I think that's one of the things that drives us as far as solar system exploration is concerned. And so for me it's where we will find a place in our solar system or beyond where life either had been in existence before or has the potential to be in the future. There's Mars, of course. Potentially Venus, now that we know you can find phosphine in the atmosphere.
Right.
And then as far as the outer solar system is concerned, we've got the moons of Jupiter. We know 3 of the moons have got liquid underneath the surfaces. And then we've got Enceladus and Titan at Saturn. And so if we're talking about solar system exploration, that for me is the next step. We need to eventually land on the surface of one of these moons and dig under the surface and see what's underneath there.
Well, you're in the middle of the intense period of planning and building one of these missions at the minute. Tell us about JUICE.
So, yes, JUICE it's a dreadful acronym. It stands for Jupiter Icy Moon Explorer. And you can get JUICE out of that. It takes a bit of work, but you can. We proposed to the European Space Agency back in 2012 that we would like a mission to go to Jupiter to essentially focus on the moons, to get an understanding about what's beneath the surface.
What's the status of JUICE now? Have you been able to keep building it during the strange year that we've had?
It's been difficult, Chris. We have been able to. Our instrument delivery is slightly delayed. We're still on track for launch in June 2022.
And so if we're looking 10 years forward, JUICE will have arrived by then, right?
JUICE is due to arrive in about November 2030.
Oh, wow, okay.
So this time in 10 years, we will have gone into orbit around Jupiter and we will be on our first big orbit.
It's going to be an exciting time. When we interview you in 10 years' time, what are we going to add? What are the big discoveries that we'll be talking about in a decade?
I think we have to talk about gravitational waves again. We're detecting black hole mergers, neutron star mergers, and the majority of it is what we would expect. And then I think looking to the future, what's really exciting is what will come out of these gravitational wave detectors now that we kind of know how to do it, how to tease those signals out, what unexpected things are we going to find.
What are you looking forward to that's coming up?
Well, I mean, I think what's very exciting is that we have better probes of the early universe. The Square Kilometre Array, which is a huge telescope with a huge collecting area. The Square Kilometre is the sum of the area of all the dishes. They're actually spread across the world, about half in South Africa and half in Australia. One of the many, many things that this array will do is study neutral hydrogen. And with this new huge telescope, it will be possible to study intergalactic gas out to very, very large distances. And in particular, at epochs when galaxies are first forming. What is so exciting about this is that this will give us a three-dimensional picture of the universe. So this will be a huge advance in cosmology, and in particular, in understanding the very early stages of star and galaxy formation.
Martin, one of the things that I'm very excited about is the ELT and the impact it's going to have. Can you tell us a bit about it and what impact do you think it's going to have?
I'm enormously excited by it as well. So the ELT is short for Extremely Large Telescope, and I
love that name.
Yeah, it's not a very imaginative name, I suppose, but it will be the biggest telescope on the planet. It's designed to have a 39-metre aperture mirror, and it's being built by the European Southern Observatory Organisation, and it's due to see its first light around 2025. It's actually being constructed in Chile right now. The largest telescopes we have on the ground now are 10 metres, the Keck telescopes, and the 8-metre very large telescopes. So the ELT is going to take us big leap forward in terms of our sensitivity and our resolution. And it's going to be particularly suited for studying planets orbiting other stars and looking into the very sort of distant parts of the universe to learn more and more about how the universe evolved.
We also have coming online very large ground-based surveys, like the Vera Rubin Observatory, which is really exciting. The Vera Rubin Observatory is going to have so much data, we haven't quite worked out yet how to store it.
It's basically going to make kind of time lapses of the sky. So it's going to be making observations of a part of the sky and then coming back routinely to get the same part of the sky again. So we'll be seeing objects, these transient events, things that happen like supernova explosions, happening in real time.
I'm at least equally excited by what's happening in exoplanet research. And this has been a hugely burgeoning field.
We've got right now for exoplanets, the TESS mission is finding more and more planets. In the future, the ESA Plato mission is going to be TESS on steroids. TESS has 4 cameras lined up to take pictures of the whole sky. Plato's got 26. So we are going all in on trying to find these planets and trying to understand how common they are. I think that our imaginations are nowhere near as good as the universe's. Absolutely nowhere near as good. Exoplanets have thrown that in our face again and again and again. So I am looking forward to being completely blown away and surprised in the next decade.
We now have thousands of detected exoplanets, but we still, except in 1 or 2 cases, the big ones, don't have any detection of the light from them. But I think with the next generation of ground-based telescopes, particularly the extremely large telescope ELT, that will collect enough light from the planet and the star that it should be possible to separate out the contribution to the light from the planet, even though it's small. And of course, an even bigger step will be to not only detect the light from an extrasolar planet, but to actually image it. And that's a long way away, but we should try and have a big space telescope which could do that sort of thing by 2068. And I said that year because that was the centenary of 1968, which is when we had the famous Earthrise picture of the Earth taken by the Apollo astronauts, which is a real iconic image. And so 100 years from there, it would be nice to have an image of an exoplanet, possibly one that's habitable.
When we look up at the night sky, can we think, oh yeah, we've got most of it sussed? Or is there still a long way to go? I'd like it if there is, because then we're still in a job.
Well, I don't know that we'll ever be there because the universe is a big place. One of the things that I've been working on is a mission called LUVOIR, which is short for Large UV Optical Infrared Telescope. And this is a concept. It's not a planned mission yet, but it's aimed at trying to answer one of the most fundamental questions we could possibly ask. And that's the "are we alone?" question. Yeah. Are there planets that look like the Earth outside in our galaxy? And can we then detect them? And can we then go and study them to understand if they're life-bearing? Now, in principle, we can do that. We have the technology, or at least the basic technological ideas. But to do it, because these objects are going to be very faint, we have to build an absolutely enormous space telescope.
So how big are we talking?
If you think about Hubble, it's a 2.5 meter mirror. The largest telescope on Earth at the moment has a 10-meter mirror. And to actually detect an Earth-like planet within a few tens of parsecs, we need a mirror about 16 meters across.
On a space telescope?
In space.
So, sort of looking at our current situation, the state of astronomy today, do you think there are challenges and problems we're facing?
What we do in terms of space and astronomy remains important. It's culturally important because it helps us understand the universe and it helps us move forward. It's also about the indirect benefits of developing technologies. Many of the technologies that we develop find application in real-world challenges. Sensors that we put in space telescopes are now in use in hospitals for medical imaging. We also feed into the economy, the space economy that has developed as a result of space exploration that started out in the 1960s is now a £15 billion part of our economy. And it will get bigger. The space economy is growing massively, and it's going to be trillions of dollars over the next few years.
So what do you think it will be like to be an astronomer in 2030 or so?
I think this is a really good time, this upcoming decade, as we've talked about all these new observatories coming online, but I think we have to recognise that it's a great time to be an astronomer if you're from certain demographics. And certainly for me, there have been so many times when I've been in a room and I've been the only person who looks like me. And so whether we're talking about someone's gender identity, their ethnicity, disability, socioeconomic background, you know, I think we need to take a kind of critical look at who's in the room, who has access to astronomy, and who's being excluded, who's being left out, and how can we make the field more open to people from all sorts of different backgrounds, because it's not on them to change to fit in with us, it's on us to change to be a more welcoming place for everyone else.
And I think we will only flourish because of that. I think diversifying sort of who's in the room for science will help us think in different ways so that we can tackle the big problems that we still do have. And I think that the big problems is the fact that there's so much that we still don't know. You know, I think there's more that we don't know than we do know. There's so many unanswered questions. From, you know, what is dark matter? I'd love to see that question answered in the next decade.
What are the big burning questions that face astronomers, and which ones keep you up at night?
Nothing keeps me up at night anymore apart from my toddler.
For me, that is the are we alone question.
The question of whether there's life out there. You know, we've had a very exciting year with the prospect of life on Venus, but, you know, whether there's life out there in the rest of the universe, on exoplanets, whether there's intelligent life, I think that's probably the ultimate question that keeps me up at night.
We're never seeing Oumuamua again, so that's going, for starters. But this was fun. A decade's a long time, it turns out.
What will the next decade hold?
Well, plenty of missions, for sure. I reckon it's just going to be a wall of exoplanets.
But for me, I want, you know, sort of a 2024, Maggie lands on the moon. 2030, Mars.
Is that the same trip, or are you coming home in between? What a decade that was, and yet there's still so much more to discover.
Do join us in January, where we reflect on how the sky at night negotiated lockdown and major scoops in our Pick of the Year programme.
Good night.